Oh, hello everyone. Here back again with the third installment on the fixed frequency 0% to 100% PWM controller. I thought maybe I glossed a little bit in the design of the oscillator section in the previous video. So I thought we'll just quickly do a detailed design of the oscillator section and basically breadboard it, right? Breadboard it and basically test how it works. That way it's clearer instead of just glossing over it, just doing a back of the envelope calculation. So let's go in detail how the oscillator section was designed basically. And if there's time, then we'll just quickly talk about the duty cycle control. It's just simply a resistor divider here shown, which basically introduces an offset to the generated ramp voltage. That way, the ramp voltage gets a DC offset, which basically allows one of these transistors here, the switching transistors here, to output a certain width of the waveform, basically. But for now, we'll just quickly go over, basically in detail, the design of the oscillator, and we'll just go from there. So, as indicated, the oscillator section is made up of a current source, which basically charges a capacitor in a linear fashion, and thereby when it reaches a certain voltage, it gets reset by a switch, which basically I described in the previous section as a back-to-back and PNP and NPN transistors connected. And the threshold is determined by this resistor divider. Basically, that's what we said. So now let's go in detail of how we design this. First of all, we're going to get the specification of the frequency and start from there. So like I said in the previous video, I wanted to trim the frequency to about 10 kilohertz. Okay, that's the oscillator is going to work at 10 kilohertz. And we talked about in previous video that the current source IC basically feeds this capacitor here, and the output voltage is, we said it was a linear ramp, and when it reaches a certain voltage, a switch resets it automatically, right? So that this is fed from VCC, so that the oscillations continue, right? So now we got a value of C here. Now, how do we know, we'll talk about how to implement the switch in a second, but now let's talk about strictly how we're going to devise a particular current C, IC, particular capacitance value C that is going to give us a frequency of 10 kilohertz. How are we going to do it? So we talked about in the previous video that the capacitor equation, the current and voltage relationship is IC with time is the capacitance value, which is fixed, and the voltage derivative of the voltage across the capacitor, right? That's what it is, right? This is just a standard, the voltage and current relationship across the capacitor. Now, what we're going to do is basically we're going to quickly show how this fixed current generates a linear voltage. So what you do is basically this is a simple first order differential equation. So what you do is you just integrate this with respect to time from T1 to T2 of IC of T dt and C, which is a constant, of T1 to T2 of the voltage derivative with respect to time, right, dt. Now when you do this, right, so the differentials cancel, or all you get is, again, this is a first order differential equation that you can quickly solve. You're going to get, and we're also going to assume that the capacitor didn't have any charge to begin with. The capacitor is in a discharge state, so the initial conditions on it is 0. So no charge across it, which means no voltage. So in that case, what you get is VC, the time, the voltage, when you see it in time, is the capacitance value, right, 1 over C when you take it to this side, divided by T1, T2, IC of T dt, right? Now, what did we say? We said that this current is constant, right? This current is constant. So if this current is constant, what you get is Vc of T equals 1 over C. Now, this current is constant. I'm going to call that constant current a value of I naught, right? So I naught is going to come because it's constant. So what you get is T1, T2, dt. And then this just basically reduces to a simple equation of Vc of T is just the constant current, right? A fixed current divided by the fixed capacitance multiplied by the simple time differential to T2 minus T1, right? So basically this holds true across any capacitor that has a linear current flowing into it. The voltage is going to rise from the time that it started to where the time finished in a linear fashion. Okay, that's all this is that's what this equation is saying. Now, if we want to use it for our application here, so what I'm going to do is I'm going to see the change in voltage across the capacitor. So the change in voltage is delta Vc, right, equals the constant current and the capacitance with the delta time, right? The delta time, the small delta time that we're going to see from the time when it started charging to a time when it gets discharged or reset, right, to the point where it gets reset. So now if we solve for, so there's two items that you can choose from here. There's 1, 2, 3, 4 variables here. Now most of them are fixed. First of all, we know the delta Vc because we said prior to, when we talked in a previous video, the delta Vc is the, as you can see, 5 volts, which is my VCC, is divided into 2 by these 2 resistors, and I get 2.5 volts here. And I'm going to go by a diode drop, which is going to be, right, slightly below, about 1.7 volts here. And then I'm going to go back by a diode, which is back to 2.5 volts. So I know the maximum voltage where this switch is going to trigger, which is 2.5 volts. So V1, where it gets reset is, I'm going to call it V2, is 2.5 volts. And then I showed you that, when this switch is going to discharge a capacitor to about the saturation voltage of this transistor plus the VB of this transistor, which was about 0.7 and then another 0.1 here and around 0.8. So basically V2 is going to be 0.8 volts. Okay? So now we know delta Vc now. Delta Vc is just simply 2.5 minus 0.8, which is approximately equals to 1.7 volts, right? So if you do this calculation real quick, right, it's about 2.5 minus 0.8, right? It's about 1.7 volts. Okay, so that's what the capacitor is going to charge and discharge to, right? Next is the frequency. Now, we know the frequency. What we are aiming for is 10 kilohertz. So what that means is the period t, which is equal to delta t, right, is equal to the period of the frequency that we're looking, right? And that would be 1 over 10 kilohertz, right? So now if we do that calculation real quick here, 1 divided by 10 kilohertz, it's approximately equal to 100 microseconds. So we know that too, right? So this is fixed as well. Now we have a choice. We can choose either one here to get our frequency, right? Either one. The specific frequencies that we're designing for. So it's always easier to choose a capacitor because the capacitor value is discrete value. We don't have all infinite, right, number of capacitors that we can choose from. So in my specific case, I had 33 nanofarad capacitor, but you can choose whatever you want, right? So you just have to adjust the current. I chose 33 nanofarad. So now the capacitance is also fixed. So capacitance is also fixed. So 33 nanofarads from my case. So now what current do we need in order to get 10 kilohertz, right? That's what the question is. So now this is again a simple linear equation. So we're going to solve for I naught, right? So if we solve for I naught, so if I can just include that here, real quick, sorry about the view. But if I solve for I naught equal to, right, delta VC multiplied by C divided by delta T, right? That's what we have. So I naught that I need is 1.7 times 33 times 10 to the power of minus 9 divided by delta T, which is 100 microseconds times 10 to the power of minus 6. And now this comes out to be about, if we do this calculation real quick, so what we get is 561 microamps, right? So now what we're saying is we have to design our current source to give us a 561 microamps into the capacitor. That is going to give us the required frequency of oscillations of 10 kilohertz, right? A ramp voltage of 10 kilohertz. All right, so how do we design the current source? Now, I showed you here the current source is also two PNP transistors to connect to back and back. And just let's quickly design this. Now, I'm using a variable resistor here to trim my frequency, which basically I'm trimming the current, this current here, right? But you don't have to use an expensive potentiometer. You could just use a resistor if you do your calculations right? You can just select a specific resistor in this current source and you get the required frequency in this circuit, right? So now let's go ahead and design the current source. Now the current source is basically you have VCC here and we got a resistor here. That resistor is connected to a reference voltage that's going to give it a VBE across it through this PNP transistor. And now that PNP transistor is buffered through another PNP transistor, like so. And now the output is here, right? That's what we designed IO. That's what we want, this current here. And we're going to connect that to here. And now that is going to be terminated by a resistor here. Now this is a specific current source topology that, you see in a lot of, electronics textbooks and everywhere, right? So basically what we have is we're going to design R, right? What's R? So we're going to call it R. So we're going to assume that our transistors have a reasonable beta, which is about 100, which is not too difficult, right? And we're also going to design this resistor here. We're going to call it R. So I'm just going to call it basically R1, this one, R2. Let's just call it that way, right? So we're going to design both of them. So now we know I naught, which is 561 microamps. So now we're going to quickly design this. Now we know VCC is 5 volts, right? This is got a drop of 0.7, and then this we got a 0.7 as well here. So what we see is 5 volts, we drop to here to 4.3 volts, right? From 4.3, we drop by another 0.7 volts, and now we get another 3.6 volts here, right? So now we know these voltages. Now what currents should we use to drive this transistor on this side? So let's take a look. Now, if it's a beta of 100, this transistor, now the base current is going to be basically this current, which is the collector current of this transistor, 561 divided by 100. So what we're going to get is 5.6 microamps is going to flow that way, right? So now what I need is, in order to maintain that 3.6, I want to ignore the contribution of this branch here, right? I want all of the current that passes through here to go through R2, right? I'm going to ignore the current that gets added from this node into this resistor. So if I am going to ignore that, in electronics, if I go an order of a magnitude in terms of current here, I should be able to ignore that. But what I'm going to do is I'm going to just, because these currents are very low, I'm going to go 2 orders of a magnitude. What means is I'm going to also make this current here the same as this current on this side here. So this current, I'm going to also call it 561 microamps. So that fixes this resistor here. So R2 So now what I'm saying is, by making this current large, I immediately ignore this current, right? It's much larger than that current, right? This current is much larger than that. I can just ignore it. So now R2 is 3.6 divided by 561 microamps. Now R2 becomes, that is approximately, so 3.6 divided by 561 microamps, we get around 6.42 kilo ohms, right? So now we're going to choose R2, a near standard value resistor, which I'm going to select 6.8K, right? I believe 6.3K is also a standard value. I believe that's the case, but I have 6.8K in hand, right? So again, that is not going to change. This is going to make this current slightly larger, which is okay. All right, so now my R2 is fixed. How about R1? What am I going to do about R1? So R1 is simple. We can see it, right? The voltage drop across it is 0.7, right? 5 volts here, 4.3 volts here. Now, what current is passing through it? Let's take a look. We said this current was 561 microamps, correct? Now, 5.61 is also routed through the base of this guy. But also this guy, remember, we chose 561 coming through here. So that one is contributing approximately 5.61 microamps as well, right? You can prove that to yourself. Just divided this current, right? Divide it by 100, you get that. So what I'm going to do is I'm going to ignore. This is contributing the same amount this way that this is contributing to this side, right? 5.6 comes in here, 5.6 comes out of here, and it's one line here. So that means is that 561 also appears here. That is the current here. So now R1 is also fixed. So R1 then is 5 volts minus 4.3 divided by 561 microamps. Now we get that. That is basically, we said 0.7, simple, right? 0.7 divided by 561 microamps, right? So sorry, it's a 6. So 0.7 divided by 561 microamps. We get about 1.25 kilo ohms, right? So I believe this is in 1% resistor. You can get this, but we're gonna approximate it to 1.2K, right? So that's the standard value. So what we have is 1.2K. So what we're gonna do is we're gonna talk about quickly how we design. Well, we know we've designed a switch, right? The switch is just simple back-to-back connected NPN, PNP transistors buffered by an emitter follower or a common collector amplifier. And we said that this was 2.5. So what we'll do is we'll build the circuit real quick right now with these values that I chose. And we're going to basically see how that circuit works, see if our calculation works. Just give me a second. I'm going to redraw this circuit nicely so that you guys can see how it looks like. Okay, so this is the circuit we just designed. This is a complete oscillator, a ramp generator that oscillates at frequency of F equals 10 kilohertz. That's what we designed, right? So this needs to be proven. We'll basically do a measurement and we'll take a look at it. Now, what are the voltages that we designed? We've designed this voltage here, right? Our voltage was 4.3. So we're gonna measure here 4.3 volts. Now we measured this, we calculated this with 3.6. This was 3.6 volts. Right, this was 2.5 volts, right? 2.5 volts, right? And then we're gonna see this VC, right? VC of T. We want to see it oscillate between 0.8 to about 2.5 volts, right? That's what we want, right? We want to see it ramp between 0.8 volts and 2.5 volts. And the time it takes to do that is, right, is a period of, or 10 kilohertz, right? Or a period of T equals, right? We calculated 100 microseconds, right? That's what we want. That's what we want to see, right? Now, there's going to be slight error in that because we didn't take into account the discharge time, right? How long does this circuit, the switch here, right? If I bring my initial calculation real quick here. We didn't take into account how long does this switch take. When it switches on, how long does it take for it to discharge this capacitor? Now, it is going to be very small, right? It's going to be very small, right? So it's not going to contribute a lot to the period here, right? So, but what you have is you're going to have slightly, your periods actually will be here. So we'll have a little bit of error, but that is, it will get us into the ballpark, right? It'll get us into the ballpark. Okay, let's build this circuit and let's do the measurements on it. Give me a second to build the circuit, and we'll use an oscilloscope to measure the frequency, look at the waveform, look at using a meter to measure all of the voltages. Okay, the process of building it. So basically I got my emitter follower transistor here, the two NP back-to-back connected switch diodes here, transistors here, my two 1K resistor and 6.8K resistor ready. So just keep building it. Okay, I just want to quickly show you that, the transistors that I'm using, most of these transistors, we assumed a beta of 100, right? So we were designing them, but they're just a lot better than that actually. So if I grab one of the PNP transistors I'm using, if I use this tester real quick here, you can see that the beta on this is, I don't know if it's going to focus. The beta is 428, so it's much better than what we assumed for our design. Let's get one of the other NPN transistors. Take a look at the beta for that guy. You can see this guy has 688, right? Beta, right? So it's so 100 is reasonable to assume. We designed it for the worst case scenario, and most of our transistors here have a better beta, so they will act much better than what we designed them for, right? So just want to show you something quick as well. I don't have 1.2K that we designed for this site. So what I decided is to use 3K and 2K in parallel. So that's the closest value I have that's going to give me 1.2K. So here is a 3K resistor, right? So I'm just going to put it here in parallel with, so you can take a look at this. There you go. It's 2.953K. And then if I put the 2K resistor in parallel with it, so just going to quickly measure it before we put it in. Just quickly measure it here. And we get 2K, right? So now if I put that in parallel with it, just a quick demonstration of how you can make up resistors with what you have. And we get 1.2K, right? So that's what I'm going to use. So 2K, 3K in parallel to get 1.2K. Okay, here is my 33 nanofarad capacitor. I don't know if you're able to read it. See if you can. Yeah, right there. And we're going to measure it real quick here. Using this handy tool. So it's measuring about 34 nanofarads, but I'm sure it's a 33 nanofarad capacitor, right? So I'll just remeasure it again here. Yeah, so we'll use that. So here's my circuit real quick to show you. So here's my two back-to-back connected PNP transistors that are going to generate the current. That's the 6.8K resistor. I'm going to measure all the values in a second. I'll just show you. So that will be connected to this guy here, and then it's going to come here. And the other side, now you're supposed to trim these long legs, but this is low frequency that we're using. It's not going to have too much an effect, but and that is going to go to ground. So if I get a longer lead here to terminate that. So this goes to ground. So my ground is over here. So now let's do quick measurements now with all the resistors here. Okay, so hope this is visible. So some of these will be slightly off because they are in circuit, right? So there is bypass capacitors here that are gonna charge or discharge during this testing, but let's just quickly test. Here's my 6.8K resistor. There you go, 6.8. There's my 1K resistor, that's the divider, right? So let's measure this real quick. There you go, it's slightly, yeah, 0.99 something. And let's do the other side from the base of this guy to this guy here. Same thing, right? Close enough, right? So that's basically what we're measuring is. So if we put this in the circuit as well. So what we just measured is, hopefully this is visible. So we just measured these two resistors. Now let's measure the 1.2K, and I showed you already, right? So I was using as the 1.2K resistor, right? 1.2K. And the 6.8K we measured, right? 33 nanofarad capacitor going to ground. So let's power the circuit up. We're going to do DC measurements, right? See if these voltages, right? These voltages that we designed are correct. So we expect 2.5 volts here, 4.3 here, 3.6 here, right? So before we do the whether this circuit oscillates or not. All right, so now the transistors I'm using are just generic, any kind of transistors that you can get, the BC 550, 450, or 545 combination of PNP and NPN transistors, or the 2N3906 and 2N3904. You can use any standard generic transistors and you should be able to, low power transistors, you should be able to get this working, right? So let's hook the power to this and then let's do the measurement. Okay, so we're gonna do the measurements. So from my power supply, I have 5 volts coming here, positive, negative, right? And I'm just gonna power it up right now. So it's powered up, and let's do the measurement now. So just give me a moment here. I'm gonna do a quick measurement here. So first of all, let's measure the power supply voltage. So my power positive rail is on top, negative rail is back here. So if I measure from here to here, what do we get? There we go. So we measure 5 volts, right? So you try to set that as precise as possible, because for the current source it's not going to have an effect, but for the voltage that this divider, it will have an effect. So set this as precise as you can, right? So all right, so now let's measure this part here. Do we get half a volt? Obviously it's just a simple register divider. Let's take a look what we get. It's this point here. Because it's oscillating, you can see actually my meter kind of detecting that, right? So the circuit is oscillating, right? So yeah, this is very so this has a high frequency bandwidth for the AC side. Okay, so there you go. So 2.5, right? So 2.513 is what we're reading. That's this voltage we just read. Now let's take a look at, let's read how much we read here. Now this circuit is turning on and off, so it'll be very hard to read this part. So I'm gonna not read this part, but just let's see what the average value is, right? So let's quickly that would be this guy here. Let's see what we read. We read about 2.1. That's the average value. There is some AC component. If I actually do that to it, because it's oscillating right now, you can see that it has an AC component. I just switched my meter to AC to read AC. Sorry, I wanted to do, what do I want to measure? That's the emitter of this guy, yes. So I'm measuring 2.2 actually. So let's see if we can read frequency. Let's see what happens if we go to frequency. Is it oscillating? Let's see. Yeah, it looks like it's oscillating about 180. I'm not sure about that. We'll have to take a look, right? We'll look in the in the oscilloscope. Now, what's the other voltage we need to do? The other voltage we need to measure is this one here. So that's just below there. So we'll go to ground and we'll go to the 1.2K resistors. So that would be the base of this transistor here. So look at what do we measure? We measure 4.23. We're designed for 4.3, right? But this has slightly less drop. You saw the beta of these transistors is really large, right? So, but anyway, so we measured 4.23 here instead of 4.3. Okay, so let's measure this point here. What do we get? We expect 3.6. Now that is right above the 6.8K resistor. So we read 5 volts. Not sure why. Just give me a second. Let me troubleshoot that. Okay, yeah. So basically, I found an error actually in my wiring here. I forgot to connect this. Basically, I forgot to connect this part here from the emitter of this switch here to the capacitor that we're charging and discharging. So that's why some of the measurements are off. So we'll do the measurements now. So, and I changed it a meter because the other meter has a high bandwidth. Actually, it does have a high AC bandwidth. So it's very flickery on the average, you know, that when you do DC measurements, it does get affected. So I'll just switch to this Fluke reliable Fluke 87 meter. So we'll just do the readings real quick. So now the power supply voltage, if you read it, it's right over here. You can see it's 5 volts, bang on. And now we're gonna do the, let's see, I'm gonna put my circuit here. I don't know if it's gonna be very well visible, but just so we can do that. And just put this back here. I'll just do this back here. Let's see, I think that's better. All right, okay. So now I'm gonna do this measurement here, the 2.5, right here. You can see it's 2.5. It's basically half the supply voltage, very simple. Now if we go, again, this is oscillating right now. So let's take a look what the measurement is here. The average voltage there, right, is at the emitter of this transistor here. Let me just move this real out of the way a little bit. So if we do that, the average is 2 volts, right? So basically that's the average. So let's see if we can do a frequency measurement here real quick. Can we do a frequency measurement here? Let's see. I'm gonna go to the capacitor. You can see actually it's about 10 kilohertz, but we'll come back to that. We'll look at the scope. So go back and measure the this here, the bottom of this current source setting resistor, the 2K, 3K in parallel. So if I do that, that would be this guy here. You can see I'm reading 4.39. We designed for 4.3, close enough. And that means around, so if we calculate the current, so we measured 5 minus 4.39. We divided by 1.2K. So actually about 500 microamps of current is flowing, not 560 something that we calculated, which is fine. And if we measure the top of this 6.8K resistor, let's do that. We designed for 3.6 and then we're getting 3.78. Again, fine enough, right, for our application, right? So you can get the purpose of this is just you do this real quick and you can trim some of these parts to get accurate values. So this is good enough for us. And if we look at the average value of the resistor, like the capacitor, we get 1.7 volts. But again, we'll take a look at the scope and then see what's measuring. What other voltage can we measure? We measure this voltage here. So these are the important ones, the ones that don't vary when this circuit is oscillating. So we've done that. Now let's turn our attention to the oscilloscope and we'll take a look at some of these voltages here. Let me set that up and I'll be right back. Okay, I'm gonna go freehand for this, sorry. So we'll do quick measurements here. Here's my circuit built again. My power supply, which you haven't seen, but you know, I'm measuring 5 volts from it, as you can see. And there's my scope that I'll use for the measurement. I'll just turn up the brightness slightly a little bit so we can see better. And basically what we'll do, so we'll start by measuring the capacitor voltage, which is the output voltage, right? Let's take a look at that. So we'll measure the capacitor, and then remember, what did we say in our calculation? So if we bring our calculation here real quick, if I can find it, actually it's right here. We said that it was going to vary between approximately 0.8 and 2.5 volts, and that it will have a frequency of 10 kilohertz. That's what we designed it for, right? So now let's take a look. So I'm going to see if we put this on the shot. So I'm going to put it where this capacitor is. So it will be right at this point here, right? The capacitor is right here. All right. So I'm going to just put that right there. Okay. So let's just do this real quick so you can see that's where it is. And here is our waveform. So now let's take a look at the waveform here. We'll do quick measurement. Frequency, first of all. So if we go to time measurement, I'm using channel 1, right? I'm using channel 1. Channel 2 is not connected to anything. It's just floating here. So channel 1 is measuring a peak-to-peak voltage of 1.7, but that's just from here to here. But ground level is down here. So you can see that the frequency is actually 10.28 kilohertz. We designed for 10 kilohertz. That's good enough. And that's close enough. And look at my cursors are set. Now cursor 1, let's go to cursor. Cursor 1, if we go here, is this one. It's, look at this voltage here. Cursor 1 is set to 0 volts. Let's see. Yeah. Cursor 1 0 volts. And then cursor 2 is, sorry, let's move it to cursor 2. Cursor 2 is going to measure the bottom of that waveform. Now if we look at the bottom of that waveform, I'm going to zoom into this circuit here and just do this real quick. I just wanted to see the bottom of that waveform. If I do that, bottom of that waveform, the capacitor is being discharged to a delta of 756 millivolts, right? We assumed it was about a VBE drop plus a VBE drop plus a saturation voltage here, which was approximately 0.8, right? 0.8. But, you know, the circuit actually is better, right? So it's discharging is slightly less than 0.8, right? So there's a little bit of discrepancies here for when we did our calculation, but good enough. Gives us a ballpark calculation now. Now let's take a look. What happens to the top? To what voltage level are we charging the capacitor to? Let's adjust our trigger level. And I'm gonna move so now if I move it up, take a look at this. My cursor is right on the top there. You can see it's about, make sure my cursor 2 is at ground. Yeah, it's at ground. So you can see the delta measurement is, sorry, the whole time I was blocking you, but the delta measurement is 2.475, right? 2.4. So you can see 1, 2, 3, 4, 5. Actually, it's slightly below 5 divisions, 500 millivolts per division. 0.5 times 5 is 2.5. Within cursors, we measure a more accurate value, which is about, as you can see, is about, the top of that is about 2.475. Okay, right, so we have indicated, just did theory, see how we got all these values, did a measurement, built a circuit, proved it to ourselves, and you can see. Now if you're curious, what does some of the other waveforms look like in this circuit? Okay, we can take a look at some of the waveforms. Now, curious, what does a waveform look like at this point here? Now, this transistor is going to turn on and off, so I assume it's going to be, most of the time it's going to, most of the time it will be off. So we'll see a constant voltage with a blip, right? You know, getting discharged and then back up, right? So let's take a look. Do we see that? If I move that to this guy here, which is at the collector, basically at the collector of this guy. So the collector of this guy is right here. That's the one. Yep, just as we assumed, right? For most of the time, it stays on. So I'm going to put channel 2 on the capacitor, so we can see the capacitance the capacitor getting charged and discharged. And I'm going to just ground reference it here. Okay, now I'm going to turn on channel 2 here. There's channel 2, so you can see it. Where's channel 2 ground? Ground for channel 2 is, as you can see here, ground for channel 2 is right there, right? So it's right there. It's the same as that, you know, if we, yeah, so that's good enough. So I think this is too bright. Yeah, that's good enough. Yeah, now I'm going to take my cursors off because they're just distracting. And yeah, okay. And then clear cursors. Now go to measurement. Now I'm going to go to 2, pick to pick. That's what we're measuring. Yeah, good enough. All right, so anyway, so you can see now, I can actually, channel 1 is getting charged. Actually, channel 2 is also distracting. Sorry, I'm just going to turn it off. Yeah, so most of the transistor, right, this guy here, spends most of its time off, but the moment it gets turned on, it pulls this voltage down to ground, right, thereby pulling the base of this guy down as well, that capacitor through there, right? That's what you see, right? Right. There will be slight time actually when we're doing our calculation. Remember I said we'll have a lot of error here that, you know, is going to contribute. That's about that, you know. So if we measure it, actually it's about from here to here is about 500 nanoseconds per division. 1, 2, 3, 4, 5. So about 2500 nanoseconds, about 2.5 microseconds, right? So, but you know, 2.5 microseconds, we have 100 microsecond period, so the error is about 2.5%, so that's okay, right? So you can see that, right? That's one interesting waveform that we see is at this point here. What other interesting waveform can we see? Well, we saw this. We can see this guy here. That guy will be similar to this guy as well, right? It's going to be mostly about 0.7 volts, right? So by the way, that voltage you can see is a diode below the 2.5 volts, right? It's a diode below 0.5. So if we measure that, turn on our cursors, and again, we're gonna put that there, 0 volts, 0 volts. Now we go to the cursor 2, and then again, it's a diode drop up below 2.5. How much is that? That will be there. You can see it's about 2 volts, right? Delta, right? So this is 0.5 volts, right? About a diode drop. Yeah, that's what that is. So let's clear cursors, go back to measurement. What else? Is there any other waveform that we can see? We can see this. Does this get affected by the switching action of this? Does this point get affected? Let's take a look. That will be at the bottom of this resistor, and that would be, I'm gonna just remove channel 2 here. Let's move that. That will be at the bottom of this resistor, which will be this guy here. Does it get affected? So it's off scale. You can see it doesn't. It stays constant, right? It stays constant. But if we zoom in, that'll probably be slight. Yeah, you can see, right? There's blips, slight blips there, right? So, but most of the time that remains constant, right? So, because it's part of the constant current circuit here. Yeah. Yeah, I hope you enjoyed this video. So basically that shows you how this oscillator was designed. And next video, we'll talk about bring back our circuit. Talk about how we set the DC offset on this waveform here. Let's go back here to the capacitor. Oh. Yeah, so basically, yeah, so go back to that. So next we'll talk about how we introduce a DC offset to this guy to control our duty cycle, right? Basically, that's what I'll do. All right, I hope you enjoyed this video. I know it's slightly long, but I'm sure some of you guys who would like to see the detail on calculation and measurement will find and appreciate this. Thank you very much. Take care. Bye-bye.